Gideon from the Department of Metallurgical and Materials Engineering at NIT Trichy. He obtained his PhD from Karlsruhe Institute of Technology, Germany, in the area of phase field modeling. And he is going to be talking about introducing and employing multi-phase field modeling to understand grain growth in multi-phase polycrystalline systems. Professor Prince, would you be okay with us recording your talk?
Yes, sir, please.
Okay, Professor Ratna, I think you can go ahead and start recording. Over to you, sir. Thank you.
Yes, sir. Thanks for the introduction, Professor Narasimhan. I first of all like to say it's a great privilege and an honor to be able to present this talk in this workshop for many reasons. One of which is it's conducted under the banner of IIT Madras, which to me is one of the best institutes for engineering in our beloved nation. And secondly, I was invited by Guru, who introduced me to this field of computational material science. Of course, I have not achieved great many things yet, but it helped me make a decent living. So thank you, Professor Kanjalla, sir. So the outset, by looking at the title, it might sound that we are about to look at a specific system and a phenomena exhibited by the system. However, the way we would reach that aspect of the talk will not be specific. As opposed to the previous talk, wherein the focus was on high-performance computing, in this talk, given the nature of the audience, wherein I believe there are a considerable amount of participants from the field of mechanics, I would like to introduce the tool, the phase field modeling, as a tool for simulating microstructural evolutions. So if you could recollect in the previous talk, it was explicated that the microstructure, they govern the properties or the behavior of the material. And we need to understand how this microstructural evolution occurs and what are the factors that govern them. And in the first session of this talk, I would like to introduce how we can do so by employing this phase field technique. And once we have done that, once we have spent a sufficient amount of time in understanding or laying the foundation for this phase field approach, we will move on to understand or to see the different applications or different systems to which we can impose or employ this phase field technique, at least where we have employed it and seen decent results. And after building up on these two aspects, we will go on to consider the system we are essentially interested in. We will see what it means in this context to be a multi-phase system, and then we will see what interesting results can be gained when we employ this particular technique to study the microstructural evolution rendered by this multi-phase system. So before getting into this talk, I would like to, at the very outset, confess one thing. During this talk, you might find a few expressions popping here and there. And based on these, please do not misconstrue me as some sort of an expert mathematician or anything of that sort. It's just that people say image or a picture, it speaks 1,000 words. And I find an equation, it reduces the number of words we use in a presentation. So I just want to make use of that. And that's the reason I've used quite few expressions in my presentation. So without further ado, let's get into the talk. So years before, there was a wonderful, or rather a decent TV show that was aired in the Western world called The Middle. This particular TV show, it revolves around a family of 5, parents and 3 kids. And the youngest one is called Brick. The Brick is portrayed as some sort of a genius, and he thinks a lot, he reads a lot. And on one Christmas Eve, he begins to question the existence of a transcendental being, God. And this he confides with his sister, and she is rather appalled. And out of the concern that if he does not believe in God, then he is not allowed to celebrate Christmas, she tries to convince him. And as you can see, he is not totally convinced. But this particular episode ends with him looking at the window as the snow falls, and he notices that these snowflakes, they have different shapes and they exhibit different symmetries. And just by looking at this and by being mystified by it, he concedes maybe there is possibly a God. I don't know how long will this bewilderment or this mystery associated with snowflakes would have carried his life, maybe till he learns about thermodynamics and few concepts in that. But similar to Brick, metallurgists, material scientists, they are also being fascinated by these structures they observe in their microstructure. So these morphologies that they observe in this microstructure. So one aspect is that they, of course, influence the property of the material, and they are also wonderful and symmetric in nature. However, the bewilderment or the question, the problem that these structures face or they produce or they render is that they are rather complex in nature. we understand the fundamental principle that governs the evolution. For instance, if these structures are observed during solidification, it is possible for us to understand, or we have understood, the fundamental principle that governs the solidification, particularly when you have a temperature gradient. And this we refer to as the Fourier heat equation. However, based on this expression, to reproduce or to simulate this structure, which is rather intricate, is not that straightforward. So one approach we can think of is first to distinguish one phase from the other. So we can introduce a condition that distinguishes one phase from the other, particularly in the context of solidification. We have to separate solid from the liquid. And once we have done so, we can then allow this interface to move. So essentially what we are doing is we are separating the phases, and we are allowing this phase or the interface that separates these phases to move. Now, when these phases move, had the shape been rather a simpler one, this approach would be easily adaptable. However, in case of intricate shapes, what we essentially need is sophisticated numerical approaches that would enable us to monitor the evolution of the interface that ultimately translates to the phase transformation, and ultimately that translates to the shape that we observe during the evolution. So the problem with having a sophisticated approach or sophisticated formulation is that it goes back to the age-old philosophical question that we refer to as the ship of Theseus, meaning if you you adapt this approach, you build a very sophisticated model, and finally you are able to create or you are able to simulate such a microstructure or such a morphology. But for the same thermodynamical underpinning, when you want to have a microstructure that is of a different symmetry, say for a 6-fold symmetry, then if you are forced to change the significant amount of your formulation or significant section of your formulation, then the question arises, is this the same model? So this posed a question or a probing question to the metallurgists who were aspiring to model such intricate morphologies. So the answer to this question came from a different domain. So what essentially happened was the idea to replace these conditions with a scalar variable came about. So the scalar variable that we are about to introduce, it comes up with its own features, meaning it's a spatio-temporally evolving one. So this scalar variable, it assumes a definite value in a given phase. For instance, in solidification, we have solid and the liquid. This assumes a value of 1 in the solid and the value of 0 in the liquid. That means by just introducing the variable, you are now in a position to separate and distinguish the different phases that are present in the system. And the interface is now, it comprises of a region where this variable, it undergoes a change in this value or exhibits a change in this value. To put it mathematically, the gradient is only non-trivial in the interface. So what essentially we have done is we have replaced this sharp interface that initially separated our phases with a diffuse one, wherein we have the monotonic change in the value of the phase field. So this variable monotonically changes from one value to another. So essentially now, when you are able to model a spatio-temporal evolution of this particular variable, essentially you will be able to model the phase transformation. So that is the concept that underpins this particular approach. Now this variable to model the spatio-temporal evolution is the second question, the next question that this approach poses. Now this variable is nothing but what we call as phase field, and that's where we get the name, the phase field modeling. Now in order to formulate the spatio-temporal evolution of this phase field that ultimately translates to the phase transformation that we observe, we formulate the overall energy density of the system. Now, the phase field, as we have seen, it helps us distinguish the phases from the interface. So essentially what we have is two different phases. That is a solid phase and the liquid phase, which we can refer to as the bulk phases, and we have the interface. So the overall energy density of the system based on this characteristic feature of the phase field can be expressed in this manner. So essentially the overall energy of the system comprises of a contribution from the interface and a contribution from the bulk phase. Now having formulated the overall energy of the system based on the phase field, now it is possible for us to formulate the spatio-temporal evolution of this phase field, which translates to the phase transformation that we want to simulate. So that can be done by considering the phenomenological minimization of the overall energy density. So what we essentially do is take the fractional derivative of it and we try to reduce the overall energy of the system. Now, it is essential to note that even though the phase field evolution reduces the overall energy of the system, we need to have a component that drives it. So we introduce that driving force by solving for the fundamental variable that has some thermodynamic significance to it. And this is coupled here, where we introduce a driving force that governs the evolution of the phase field. So you have the driving force that arises from the bulk contribution, and you have a separate interface contribution. So that largely handles the curvature. So essentially, what we have done is we have introduced phase field, we have distinguished the overall system into bulk and interface, we have formulated the overall energy system in terms of the bulk and the interface, and then we have now able to model the phase transformation by just modeling or formulating the spatial temporal evolution of the phase field and coupling it to the evolution of the fundamental variable. Now, if we introduce the anisotropy to the interface contribution, then ultimately you will end up formulating the phase transformation that renders intricate morphology as we see in a dendritic microstructure or in the other case, the snowflake structures. Now, once we were able to address this particular question of modeling solidification with intricate structure, then the shift was to modeling the similar structures or similar phase transformation in isothermal system, wherein the driving force was largely governed by the concentration or the supersaturation of the concentration. So before proceeding in that direction, it was essential to observe the characteristic feature that was associated with the overall free energy density. So if you look at the overall formulation of the free energy density, it is vital to note that the contribution of the bulk phase, it is sufficiently separated from the contribution of the interface. So you don't have any influence of temperature on the interface free energy density. So this is one of the features that renders thermodynamical significance to our phase field approach. So before proceeding to the question of employing the same approach to model phase transformation in isothermal system, wherein we have supersaturation in concentration, it needs to be ensured that we have sufficiently decoupled the energy contribution from the interface from that of the bulk phases. So the initial response to this question of modeling the phase transformation in an isothermal system was just to replace the temperature with concentration. So after all, when we replace the temperature evolution in the Fourier's expression with concentration, we ultimately end up with Fick's second law. So when this approach was adopted, it was soon realized that the thermodynamical consistency that was rendered by this approach through the decoupling of the interface contribution and the bulk contribution was compromised. So we have concentration, a variable with thermodynamic significance, influencing the interface energy contribution. So the next question was to get rid of this particular coupling that we observe when we use concentration as the fundamental variable. So the answer to that question was to introduce the phase-dependent concentration. Instead of having a single variable to deal with a system of two phases, and that has only one independent variable, we need to have two different concentrations, meaning the concentration that are associated with each of the phases. So that's the reason why we have, instead of a single concentration and a single concentration dependent phase field formulation, we have these two different variables that govern the phase transformation or that govern the model that render the phase transformation in a system wherein the supersaturation governs the evolution of the phases. Now, when we introduce such an approach to get back to the thermodynamical consistency offered by the phase field technique, the problem, or one needs to understand that these variables are unknown at the interface. So we are able to formulate the free energy densities of individual phases by considering these phase-dependent concentration. However, in the interface, we have combinations of phases. We don't have any one distinct phase that are present in the interface. So one needs to find out these or ascertain these values at the interface, because ultimately it is the interface that governs the evolution of the phases. So therefore, two different conditions are adopted in order to calculate these, ascertain these phase-dependent or know the values of these phase-dependent concentration. So one involves a recreation of the continuous or the interpolation of this phase-dependent concentration. The other involves assuming an equilibrium between these two phases within the interface at testing point. Rather, a local equilibrium is assumed. So we have two unknown variables and a set of equations that can be employed to calculate them. So this approach is largely employed in commercial softwares as well in order to model the phase transformation in a system, an isothermal system, wherein the supersaturation and concentration largely governs the evolution of the phases. However, the trade-off here is, or rather, before going to that, when you employ such a fundamental variables, that is phase-dependent concentration, the evolution of the phase field still remains, the overall formulation of it still remains the same. However, the concentration evolution that governs the phase transformation is now rather extended because we now have, instead of one variable, two phase-dependent variables. Now, when we adopt this technique, even though it renders a thermodynamical consistency to your approach, the trade-off that we give away is that it increases the computational burden of your model. Meaning, for every interface that you face, like for instance, if you consider a polycrystalline system and you have numerous grain boundaries, and in these grain boundaries, if you want to calculate the driving forces, then correspondingly, the computational burden that you impose on your system also increases. So the next task was to find out an efficient way to find these unknown phase-dependent concentration. So this was found out in an elegant manner by considering the relation between the concentration and the free energy density. So if you could recollect, the relation between the concentration and the free energy density is in the form of a parabola, and the first derivative of it is the chemical potential, and that gives a linear relation. And based on this linear relation, you can directly calculate from the chemical potential, if it's known, the phase-dependent concentration. And this gave rise to what is commonly acclaimed to be an efficient approach called the grand potential technique. So essentially what we have now done is we have replaced the phase-dependent concentration as the fundamental variable with the chemical potential as the fundamental variable, basically because we want to reduce the effort that goes into calculating the unknown phase-dependent concentration. Now, once we change the variables, the correspondingly the evaluation equation that governs phase transformation also changes. So essentially, you have a similar formulation for the evaluation of the phase field. However, since we don't have a canonical equation for the evaluation of chemical potential, we derive it by considering the dependency of concentration. So concentration now depends on, or the continuous concentration depends on the phase field and the chemical potential. Now using the chain rule and rearranging this term, we will be able to ultimately calculate or formulate an expression for the temporal evolution of the chemical potential. So having now formulated a model that is thermodynamically consistent because we have a clear decoupling between the interface contribution and the bulk contribution. And now we have made, to some degree, this approach to be efficient by introducing the chemical potential as the fundamental variable. We can then move on to consider different systems wherein this approach can be adopted to simulate microstructures. Now, one of the systems is the obvious one, which wherein the problem of phase field modeling gained is impedance. So that is the growth of dendritic structure, a three-dimensional one. And this we can elegantly, or we can with certain degree of efficiency do using or by employing this approach. And a quantitative driving force to the bulk contribution can be rendered by introducing or appropriately incorporating the data from the CalPAT database through by employing softwares like DTRA, Thermocalc, and Pandat. Now, there is only a few things that you can do when you are just able to consider, or your formulation constrict, or rather restricts the consideration of number of phases in your system. Supposing we have a well-known microstructure evolution, which we refer to as the growth of Perlite, which is wonderful because it's a cooperative one. The carbon that is injected by one of the phase is being absorbed by the other. So you have a cooperative growth of the two phases. So such system, it demands, so it involves more than two phases. It involves rather three phases. So you have to render sufficient consideration, or your phase field variable or the scalar variable that you use should be sufficiently sophisticated in order to accommodate these three different phases. So when you extend your model by appropriately treating the phase field, then you will be able to simulate such a phase transformation where we have the evolution of more than two phases. And using that approach, we are able to simulate the growth of Perlite, wherein in addition to the evolution of the phases, we can also see the evolution of the concentration that generally renders or governs this evolution of the phases. Now, like similar to the phase field that restricts your system that you can approach using the phase field technique, the number of components that you consider also restricts, meaning so far what you have been considering involves just one independent variable. So here we have just seen a FEC system, meaning iron carbon system, and the one independent variable is the carbon. Supposing if you want to extend your approach to a system where are more than one independent variable, then correspondingly the treatment that you render for chemical potential should also be extended. So when you offer such an extension to the treatment of the chemical potential, then you will be able to model phase transformation that are associated with, say, ternary system. And it is important to note that whatever treatment that you render for the chemical potential should also be extended to the phase-dependent concentration that are involved in the formulation. Now, if when we make our model sophisticated enough to include more than one component and more than one independent phase field, then you would be able to model these transformations such as these, wherein we have 3 different phases and which are governed by evolution of 2 independent concentrations. Now, one the advantage of employing the phase field technique in addition to modeling these phase transformation is that it helps us to understand the governing principle of certain phase transformations that cannot be to great accuracy ascertained from experimental observations. So one such evolution is the growth of divergent perlite. So this growth of divergent perlite is unique because unlike the growth of regular perlite, which is steady state in nature, and as you can see, or as you have seen, it is the growth of these phases are rather parallel. In case of divergent perlite, this is observed in this manganese steel. The growth is not steady state. There is a decrease in the driving force as the phases begins to grow, and this decrease in the driving force, or this decrease particularly in the concentration of manganese, it drives the evolving phases to diverge in search of this manganese, and this can be modeled provided you have introduced sufficient or quantitative driving force to your model and you have appropriately treated the chemical potential to such intricate phase transformation wherein it's not steady state and it depends on the concentration of the manganese and other chemical components that are available in the matrix. So those minute or those influence can also be reproduced in such a simulation. Now, so far what we have considered is, we have considered the bulk driving force to be largely be synonymous to that of the supersaturation that is rendered by concentration. Now, in addition to that, it is possible for us to also introduce some elastic driving force to define our the bulk contribution in such a way that it is possible for us to introduce an elastic driving force. Of course, since we are talking in terms or in the context of the phase transformation, the elastic driving force is not solely the one that governs the evolution of the phases, but it is the one that renders morphology to an evolving phase. So in this case, the driving force is not the evolution of the concentration. The driving force is a constant one, but the morphology of the evolving phase is rendered by the elastic driving force. And using this approach, we were able to model the growth of martensite in a polycrystalline system. And the one given the nature of our formulation, since we have introduced the elastic driving force here instead of anisotropy to render the morphology, we were able to also incorporate the autocatalytic nucleation of the energetically favorable variants during the growth of martensite. So what we have from the phase transformation purely governed by the evolution of concentration, now we have modeled the displacive growth of martensite, or diffusionless growth of martensite, wherein there is no evolution of concentration, but it is governed by a constant driving force, but the elastic driving force, it gives a particular morphology to the evolving phase. And now it is also possible for us to combine the chemical driving force and the elastic driving force in such a way that the evolution of concentration allows for the growth of the phases. And again, the elastic driving force, it gives a shape to the, or a morphology to the evolving phase. And one such example is the reconstructive growth of Wittgenstein ferrite. And as you can see, we have the evolution of concentration that renders, that drives the growth of the phase, the ferrite phase, and it's the elastic driving force that renders its shape. Now, even though these observations or these observations are largely indicative of the influence of elastic driving force in terms of its morphology, its influence on the morphology, it also helps us understand the growth of certain plates which are mutually accommodating. So whenever the undercooling is small, whenever the supersaturation is small, in a physical system, we observe the growth of such plates wherein we have mutually accommodating 2 different variants. We found that these mutual accommodation reduces the elastic driving force that opposes the growth of the phase. And such observations we were able to make by combining the chemical driving force and the elastic driving force in rather a bigger manner. Now, so these are the wide range of systems wherein we can apply. So beginning with a system wherein the evolution is purely governed by the diffusion of concentration, and a system wherein it is diffusionless transformation, and a system wherein we have combination of elastic and chemical driving forces. Now, to get back to the problem or the system that we are, or this topic deals with, we want to study the evolution or the grain growth in multi-phase system. So in this context, the term multi-phase system has a different meaning than a general one. So if you consider a polycrystalline Pearlite structure, even this can be referred to as a multi-phase system because it has more than it has two phases and it has several grains associated with it. But the problem is, despite having different grains, the chemical composition of each of these grains are rather similar, so we can refer to it as a homogeneous system. And the overall grain growth in this system, for instance, is largely governed by the evolution of the grain boundaries. As opposed to such a system, we have a multi-phase polycrystalline system wherein the phases or the grains are not chemically homogeneous. The grains assume a particular constituent phase. So one grain need not be chemically homogeneous to another grain. So its concentration can be different from the other. So such grain is in this context what we refer to as the multi-phase system. So the grain growth in such a system, it indicates all the characteristic features of the grain growth, meaning there is an average increase in the or there is an increase in the average grain size, and there is also the movement of the interface. There is a reduction in the total number of grains. However, despite all these, we have to preserve the volume fraction of the phases. So that is the challenge we face when we intend to model the evolution of such a system, where you have a polycrystalline system with numerous grains, and each of these grains are chemically, they are not homogeneous, they are distinct. So in conventional cases, when you want to model grain growth in a multi-phase field or a multi-phase field approach, the bulk contribution is ignored. And it is reasonably done so because the overall grain growth is largely governed by the movement of the interface. It is a curvature-driven process. But in consideration, or when we want to look into the multi-phase polycrystalline system, certain extension needs to be made for this in this model. The first extension is we need to appropriately treat your phase field. So the phase field cannot be indicative of a chemically homogeneous grains, but rather it should distinguish alpha grains from beta grains and so on and so forth. And secondly, and more importantly, we need to have or introduce an appropriate driving force that enables the preservation of the volume fraction. So by combination of these two conditions, we will be then able to model the grain growth in a multi-phase system that is quite different from a grain growth in a homogeneous system. And this is by adopting this approach, we will be able to see how the evolution of grains are. Now, we want to see how the kinetics of these evolutions vary. And for that, we plotted the change in the average radius of the system with time. And as you can see, with the introduction of the second phase into the system, thereby establishing a duplex microstructure, the kinetics of the evolution is significantly reduced. But in order to be absolutely sure about what is the governing principle or what is the fundamental mechanism that governs the evolution, we considered this average radius, raised it to different powers, and then related it to time, and then calculated it correlation coefficient and illustrated it graphically. So as you can see, in homogeneous system, the highest degree of correlation is observed when the average radius is raised to the power of 2. And the highest degree of correlation is observed in a multi-phase system when n, the exponent, is equal to 3. So that means that the evolution in the homogeneous system is rather governed by the movement or the mobility of the interface, whereas in case of multi-phase system, it is governed by the diffusion of the chemical components that are involved. So these indicate the change in the mechanism that operate during the grain growth in multi-phase system compared to the homogeneous system. Now, in addition to that, the duplex system also offers us a setup wherein we can consider the grain boundary energy anisotropy, meaning in a duplex system, we have 3 different grain boundaries. One that separates grains of identical composition, and the other that separates grains of different composition. So just by considering these, or just by considering different values for these different distinct grain boundaries, we will be able to introduce a certain degree of anisotropy in the grain boundary energy. For that, we can consider constants like R alpha and R beta, and supposing we assume they are equal to 1, it renders us a microstructure. The model renders us a microstructure which comprises of the characteristic features like grain boundaries and triple junctions. However, when we introduce a certain degree of anisotropy, then in addition to the triple junction, we are able to observe junctions wherein 4 grain boundaries meet. And these junctions are now referred to as the quadruple junctions. And these number of quadruple junctions, they increase as we increase the anisotropy in the system. And these quadruple junction, in addition to rendering a good image, they also influence the kinetics or the growth kinetics that the multiphase material exhibits. So this, we played around with different anisotropies, and we observed that at one instance, the major junctions that are present are no longer triple junctions, but quadruple junctions. Now, if you consider a phase transformation as a spectrum, wherein at one end you have an evolution of phases that are largely governed by the diffusion of the chemical components, and at the other end you have a diffusionless transformation. This whole spectrum of phase transformation can be modeled in the framework of phase field approach, in addition to the grain growth in a homogeneous system and also in a multi-phase polycrystalline system. So with this, I would like to wind my talk up. So thank you.
Thank you very much, Dr. Prince. So we have a couple of minutes for a few questions. So if anybody has any questions, so please raise your hand at the yeah, Mr. Girish Khanna has a question. So Mr. Girish Khanna, I think you should unmute and
hello, sir. Sir, I have one doubt regarding high entropy alloy. Suppose if we have high entropy alloy solidification, if I am doing some 7-component high entropy alloy during vacuum arc melting process, can we do, is it possible to do good phase field simulation for this kind of 7-component high entropy alloy during vacuum arc melting process?
Provided we have a good CalFAT database, in the sense the driving force that we introduced in this phase field framework, it all comes from, or we make it quantitative by introducing the database that is established. Supposing you have an high entropy database for high entropy alloys, then it should be possible for us to incorporate that database into our model.
Okay, sir. I thought it is very clearly can we discriminate that whether what kind of phases will be found after doing CalFAT approach or after the microstructure level. I'm asking. Suppose I have some eutectic component high entropy alloy. After doing CalFAT calculation, I am trying to synthesize it. While doing vacuum arc melting process itself, is it possible to simultaneously do this simulation and then validate with experimental and this data? We can compare and is it possible to publish some article? Because I am working on it. That's why I am interested to ask a doubt regarding it.
Yeah, it should be possible, and it was evident, I believe, from previous talk by Professor Fani Kumar, wherein he explicitly showed that he was able to relate the experimental results with the simulation ones. So yeah, simulated ones rather. So of course, it is possible to do.
Okay, sir. Thank you, sir.
Anytime.
Thank you. Are there any other questions? So I have a quick question. So when we are trying to suppose you said that you can also include the effects of elasticity in order to control the morphology or in order to predict the morphology of these the evolving phase fields, right? Or so suppose there are problems where the mechanics is such that you are also inducing some plasticity. What would be the appropriate term that you have to add to the free energy function in order to account for that?
Okay, so one, I don't know, the wonderful thing about the framework of phase field is that it all depends on how you build your overall energy of the system. So like we have seen, we have definite blocks. So in the bulk contribution, we can introduce the chemical contribution and also elastic contribution. And in that as well, you can introduce the plastic as well. And you can couple these two different driving forces. So it is also possible for us to couple it, and thereby we have the influence of both elasticity, plasticity, and it is being, of course, driven by the evolution of the concentration. So it is possible, and people have already done it.
I see. Okay. Thank you very much. Are there any other questions? Okay. If there are no other questions, let's thank the speaker once again. Thank you very much, Dr. Prince. And I think we can move over to the next speaker.
Narasimhan, sorry. There is a 20-minute break.
Oh, I see. Okay,
Yeah.
so we have a 20-minute break before we start with the next. I see. Yeah, the next talk is at 17:40. So we will assemble here at around 17:35. Yeah.
I think Anand, don't close the meeting. You please keep the meeting on and then let people come back in 20 minutes.
Yeah. Everything will be as is. We'll just reconvene at after 20 minutes break. Okay.
In the meantime, maybe we can check the next two speakers' connection, the screen sharing and audio, just to be sure. Yeah.
Dr. Ambati, would you mind just sharing your screen and so that we can make sure that it is visible?
Yeah, sure.
Thank you.
So, can I share it already? Right.
Yeah, I made you presenter. I made you presenter.
Right.
You can try. Yeah.
Right.
Yeah, I think it looks fine. Can you make
I think we can also check for Dr. Srikanth as well.
Yeah.
I'll make Dr. Srikanth a presenter. Yeah.
Sure.
Dr. Ambati.
I can try now.
Yeah. I made you presenter, Dr. Srikanth.
Okay.
May I try once again?
Yeah, I think it's fine. I think Dr. Ambati, your thing is fine, looking fine.
Okay.
You want?
Nice,
Yeah.
thank you.
It looked fine. Yeah.
Okay.
Does that work?
Yeah, I think it's
It's
fine.
fine. It looks fine.
Okay.
All right. Thank you very much. So before we proceed, I think we have already. I think Professor Ratna has already contacted you regarding this. So we do have your permission to actually record these.
I think Professor Narasimhan, Dr. Ambati doesn't want his presentation to be recorded. I think Professor Srikanth, I think, can we record your talk or?
Yes.
Okay, good.
Thank you.